Robotics is definitely one of the most promising applications for neuromorphic computing technology. Several examples have shown how efficiently different capabilities can be implemented on our neuromorphic research chip Loihi. These are such examples as fast sensory learning, as for instance learning to recognize orders after just single-shot presentation of a target order, or learning to classify different objects based on combination of tactile and visual information, both represented as a stream of events, or such capability as forming a map of the environment, like in simultaneous localization and mapping task, which also has been shown to run 100 times more efficiently on neuromorphic chip than on a GPU solving an equivalent task. Although these individual capabilities are really promising and compelling, still the field faces a challenge of integrating all these different systems and networks into single architecture that could control such a complex robot as the iCub.
The idea behind the robot is that we can compare how a child might learn and a robot might learn, and understand how we can give the robot the same abilities as a human child. Our research looks at how the mode of computation, in this case neurons implemented in silicon, can help a robot like this to learn and understand the world around it.
What is this called?
iCub, that's a box.
Oh, I see. This is a box. Let me have a look at that.
Can you show me the box?
Here is the box.
And what we want to do in collaboration with Intel is to understand how we can interface these biological sensors with a biological processing device.
So which are the parts that we have integrated so far? First, of course, it is object recognition. So the ability to memorize a number of object instances and be able to recognize them in the environment. We managed to do this very efficiently and enable very fast learning by making the respective network small. How can we still solve the task and have a small network? There are two tricks that we use. The first, we rely on event-based vision combined with microsaccadic eye movements that filters out visual information so that we receive already sparse stream of events that is preprocessed and can be then processed efficiently on neuromorphic chip.
The neuronal state machine controls activation and deactivation of different behaviors, such as looking, recognizing an object, or learning a new object. Each behavior is activated or deactivated as appropriate in the current context.
The second bio-inspired trick that we use is attention. We have a module running in the background that selects potentially interesting portions of the visual field and directs robot attention, both covert and overt attention, to this part of the visual field, so that now computing resources can be focused on processing these parts. And then you simply require less neurons than you would need to process the whole visual stream.
The objects are learned and recognized by a convolutional spiking neuronal network on chip. The network is driven by events generated during a microsaccadic eye movement. Different poses of the object can be learned on the fly.
So apart from object recognition, we also integrate spatial memory. So this is the ability to remember where the recognized objects have been seen previously, and an ability to query this representation. So to remember where the object has been seen last time and to detect if the object has been moved in the meantime. So these shifts and movements can be detected and reported to the user. Moreover, the spatial map can be constantly updated if environment changes or if the errors are detected and need to be corrected. And the update happens on chip using local plasticity or learning rules.
The locations of objects are stored by a network that tracks the heading direction of the robot. The head poses are stored during learning and can be recalled later in order to detect any changes.
The third component that we integrate here is a state machine. So part of the overall state machine that controls behaviors of the robot runs on chip, and this neuronal state machine not only triggers some of the behaviors of the robot, it also reconfigures the neuronal networks on the fly depending on the behavioral context. There's still, of course, a lot of work to do, and we plan to integrate more behaviors and more capabilities in this architecture. One obvious addition is to add 3D vision capability so that the robot can also estimate the pose of the object and its size, its shape, in order to be able to guide actions toward this object and enable manipulation in the future.